Okay, so now we're going to continue talking about limits, but now we're going to go into the book and really look at the kind of things that you're going to be expected to do for this class in the book. Why do they have a picture of a leaf being eaten by caterpillars? I don't know. I find it kind of disturbing. But that's where chapter 2 starts. Remember, the book is posted online. Go to the website and click on textbook and then scroll down to chapter 2. I highly encourage you to read through all of section 2.1. There's a lot of important information there. You know, it's good to get used to reading textbooks. So if you look at starting at page 59, there's an example that has to do with finding average speed and instantaneous speed. That's exactly what we just went through. So you're going to see how their situation is similar to ours. They use a little bit simpler equation. Here's our definition of the limit from page 60 that I already shared with you guys. And now the next thing that we're going to look at is this example they gave here. So they gave example of these three functions. So you have x squared minus 1 over x minus 1. So one thing you want to notice about that function, x squared minus 1 over x minus 1. So if I have x squared minus 1 over x minus 1, right, you can factor the numerator of that and have x plus 1, x minus 1, and your denominator is x minus 1. All right, so what you want to notice is that you can cancel a matching factor in the top and bottom and say this equals just x plus 1 as long as x does not equal 1, because x equals 1 is where the whole is. So x equals 1 is a whole. All right, so this is, now this function y equals x plus 1 is just a line, it's a linear equation. The slope is 1, the y-intercept is 1. So that is why the graph that you see here is a graph with slope 1, y-intercept 1, and a whole at x equals 1. All right, that's the graph of this function that they gave here. Now, one thing that they could do is say, okay, where the whole is, we're just going to define a value. So this is a piecewise defined function now. So when x is not equal to 1, we're going to go with this function, and when x is equals 1, we're just going to assign the value 1. And notice that 1 is not where, it's not on the line. So you have, we have a whole, and then we have a point defined for the function, but the point defined for the function is different from what's in the whole. All right, now these are three different functions they're comparing. So the third function is just x plus 1, just what we'd get if we would reduce this function. So now this is just x plus 1 and there's no whole at all. So in these three functions, they're saying that the limit as x approaches 1 of each of those three functions is 2. So here's 2 up here. So whether there's just a whole there, or there's a whole with a point randomly defined somewhere else, or there's no whole, in either case, the limit of that function is 2. So let me talk about that a little bit more generally and why those limits are what they are. So we could say, sort of in a general sense, I have some function, doesn't have to be linear, it has a whole in it, all right? Or I have a function, it has a whole in it, and it has a point defined somewhere that's vertically aligned with the whole. Of course, if I put an extra point that's not vertically aligned with the whole, then I would have two different y values for the same x value, and what I would have would not be a function. So if I'm going to define a point out of the whole at all, there has to be a point that is vertically aligned with the whole, or else the graph will not represent a function. All right, and then here's the other possibility. All right, so sometimes we'll put a point there just to indicate that we didn't have a whole, but of course you wouldn't have to. All right, and so let's say then, contrasty color, that this is x equals c in each case. And let's say this is L in each case. All right, so in this case, we say the limit as x approaches c of f of x equals L. This is true in all three cases. The limit as x approaches c of f of x is L. The limit as x approaches c of f of x is L. Now what you have to do practically for this class is you have to be able to look at this situation and say that limit is L. All right, so or if you see this, you know, and like there's a 3 here and it's 4 right there, you have to be able to look at that picture and say the limit as x approaches 4 of f of x is 3. That's what you have to be able to do. Or if you see this, you're going to say the same thing. That's the kind of question that could be on a test. All right, now What's not going to be on the test is epsilon delta stuff. Anytime we talk about epsilon delta, it's not on the test, but it's important for understanding. So I want to show you why in all three cases the limit is L. Like why in this case is the limit not C, right? So for example, if I have here limit as x approaches 4 of f of x is 3, and let's say this point was up here at 5, okay? Why don't I say the limit as x approaches 4 of f of x is 5? By the way, it is true that f of 4 is 5. In this case, but the limit as x approaches 4 of f of x is 3. Why? What's the difference? So f of x means what's the actual value of the function? Where's the graph? In this case, f of c does not exist. It's undefined. Right? If this point is let's call it y1. In this case, f of c is y1. And in this case, f of c is L. So f of c is whatever the y-coordinate is. But the limit as x approaches c is where the hole is. All right? So why that is essentially, like if you think of small epsilon bands here, you can always create a small delta band that's going to contain all the point values. And you can make that containment area be smaller and smaller. And you're always going to contain function values within that. Those epsilon and delta bands, right? Remember, this is an epsilon band. This is a delta band. And you can crush that all the way down to the size of that hole, remembering that the size of the hole is 0. Now, if you look over here at this one, if you create an epsilon band around the hole, okay, the epsilon band does not contain the point. It contains the hole. So that's why the limit as x approaches c is L, not y1. Or in this case, the limit as x approaches 4 is 3, not 5, because the epsilon band encloses the hole, not the point. All right, so that's in your epsilon bands get smaller and smaller, blah, blah, blah. All right, over here, your epsilon band does contain the point just because it happens to be on the function. So this is like just a very rough discussion of why, you know, your definition of epsilon and delta bands tells you that when you talk about a limit, you're talking about where the hole is, but when you're talking about the function value, you're talking about where the point is. Now, if the hole and the point value are the same, you could think of it like this. If there is no hole, then the hole and the point value are the same. The limit and the function value are the same. So for example, if I had this function, and there's no hole in it, right? So if I had 3 here, and let's say this was 5, okay, I would say the limit as x approaches 3 of f of x equals 5, and I would also say that f of 3 equals 5. And the fact that they're the same says something important about the function. We'll talk about more next time.